Hayalperestlerin, risk alanların, denemekten korkmayanların cesaretinden doğduk. Bizi asla yarı yolda bırakmayan o sesin rehberliğiyle ilerlemeye ve öğrenmeye devam ediyoruz. Bunun için varız. Bu yüzden gece geç saatlere kadar lambalarımız sönmez. Elveda demek hem hüzün hem de gurur verir. Her şeyi sorgulayarak ve merakımızı besleyerek, dayanıklılığımızı test ederek, sınırlarımızı aşarak, ilerleyerek ve yeni ufuklar açarak yeni bir yol buluruz. Yeni icatlar çıkararak, kendi yolumuzu çizerek. Burası fikirlerin doğduğu ve yeni fikirleri doğurduğu, bizim de doğduğumuz, birlikte büyüdüğümüz ve yükseldiğimiz yer. Burası Yakın Doğu Üniversitesi.
Hello everyone, welcome back after our break. Welcome to Room 1, Session 2. So in this session, we're going to have 6 presentations. We'd like to start by our first presenter, Dr. Hamza Said, that will going to be present the paper title, Compressibility Characteristics for Hydrocarbon Contaminated Beach Sand Under Static and Repeated Loadings. Yes, Dr. Hamza, you can start your presentation. Welcome and thank you.
Thank you very much. Greetings to all. I'm Hamza Said, the PhD candidate of the Geotechnical Engineering in the Eastern Mediterranean University. So today's topic is going to be related with the compressibility characteristics of hydrocarbons contaminated beach sand under the static and repeated loading conditions. So before delving into the presentation, here is the brief overview of the presentation. I will start with a brief introduction of the contaminated soil behavior, which will be followed by the materials and methodology. Thirdly, I will present the results and the discussions of the investigations we have carried out. And finally, I will conclude the presentations. So in this slide, there is a figure I have pasted, which is a famous example of the hydrocarbon contamination from the Exxon Valdez oil spill. And this occurred almost 30 years ago, and still there's a lot of lessons to be learned, because still at some locations, the oil patches are still over there. So soil contamination has become a critical issue. Along with it, it became a globally recognized issue, because anything apart from water into the soil structure is a problem, and it's like we have to identify what sort of problems that can occur. So generally, when we talk about the contaminated soil, there are 3 major role players. For example, hydrocarbons. In other words, this is related with the petroleum contamination, heavy metals, and we can also have other organic and inorganic compounds. So in figures 1, 2, and 3, these are the scan electron microscopes of some of these contaminants which are present in the soil. And Exxon Valdez oil spill, which I was talking about earlier on. So here is, for example, one of the trench was dug, and we can see that still there is the oil present after even almost 30 years. Like in 2018, some researchers were carrying out some investigation, and they still found out patches of oil contamination into the beach soil. So hydrocarbons are basically organic compounds, and they exist in nature either as a solid, liquid, or gas. They have generally the simplest atomic structure, which is composed of the carbon and hydrogen atoms. And along with their simplest atomic structure, they are classified into 2 categories, which can be aliphatic or aromatic. So generally, aliphatics are the heptane, and these are like branched shaped atomic structure, as we can see in the figure 4. Whereas the general use we can use, for example, use in our daily lives, such as automobile and other transportation purposes, benzene, which is basically the aromatic, which is a chain-like structure over there. So here are the full classification of the hydrocarbons, as I mentioned earlier, classified into aliphatic and aromatic. and along with there are sub branches as well. So how does the hydrocarbons can affect the soil? So for example, in the figure 7, this is the scan electron micrographs of the illite clay mineral, as we can clearly see that. And if we see that these are all at the same scale of 5 microns over here, that the structure of the clay has completely changed. So for example, we know that the clay structures are plate-like shaped, and if this is our clean clay soil, can see that, for example, how the particle arrangements are occurring over here. So for example, here, the particle orientations are majorly, for example, face to edge dominated. Whereas if the contamination rate is increasing, we can clearly see a difference that, in fact, now the dominant particle to particle orientation is face to face or edge to edge over here. So for example, if the clay structure is dispersed, it is converted to the flocculated structure, and also if the clay is in flocculation, it can be converted into a dispersed state. So this is how the hydrocarbons can affect the structure of the, or I should say, the clay matrix of the soil. Whereas when you talk about the hydrocarbons contamination in the cohesionless soil, we can see that, for instance, it is directly affecting the particle morphological characteristics. For example, if this one is our clean Ottawa sand in the figure A, if the rate of contamination is increasing, the rough surface of the sand is completely converted into vitreous state. Another thing is that here the rate of the contamination plays an important role. For example, it might create a heterogeneous structure. For example, over here, some of the particles are being covered with the hydrocarbons, whereas some of the particles are still in their rough state. So it will cause a slippage between the particles, and as the contamination rate increases, more and more slippage might occur. So coming towards the materials and the methodology of our experimental investigation, we collected our soil samples from the Famagusta Bay. So here is the particle size distribution curve of the carbonate sand Famagusta Bay. So the sand has approximately from 0.4 to 0.6 grams in each gram of the sand as a carbonate content. And here is the magnification of the sand particles we have taken from the Famagusta Bay. As we can see that it is quite a wide range of particle shapes are present in the matrix. So we prepared our specimens in terms of the funnel deposition techniques, and we reconstituted our specimens as 35 and 70% relative densities. And we have added the contamination as the petroleum hydrocarbon, which is classified as gasoline, as 3, 6, and 9%. So we have artificially contaminated our carbonate sand, and we have added in such a way that the targeted relative density is not changed, as we can see in this phase relations of the clean and contaminated sand. And here are the hydrocarbons properties which we have utilized and contaminated our sand with. So here is the experimental investigation rundown. We have added the contamination levels were set as 3, 6, and 9%. And we tested our specimens in dry and saturated state. The point of focus of this presentation will be the one-dimensional compression test under the stress-controlled conditions. We applied the static and the cyclic loading as well. And at the end, I am going to discuss the compressibility characteristics of these experimental investigation. So coming towards the results and discussion part, the first thing I'm going to discuss is how the contaminants have affected in the dry state. So for example, if we look upon the loose state, this black line is representing the clean sand. And as we added the contaminants, the compressibility behavior increased at 3%, and 6% showed the highest response of the compressibility. Whereas interestingly, when we added the 9% of contamination rate, it moved upward. So although we can say that here it might have improved, but when we are going to discuss later on the inside details, critical details, like in fact, this might not be like a positive behavior at higher contamination rate. So similar response was generated at the dense state. We started to add contamination. It increased the compressibility behavior at 6%. The highest response was recorded, and then moved up. So if we analyze the comparative behavior, so this is the whole range of the maximum and minimum void ratios, and we can still see that all the specimens are within this range, which indicates that we are still in the pre-crushing behavior of the soil in all cases over here. So here in this figure number 12, we can see how the compression index is varying across the contamination rate. So for example, it's start to increase at 6%. It is the highest compression index was recorded, and then it started to decrease. This is both cases in loose and dense state. So here are the values which we can see that at the 6%, the highest, in fact, both the compression index and rebound index were recorded. Although the higher rebound index is generally associated that the soil has most elastic recovery, but when we take the ratios, in fact, that is not the case. Even the 6% shows the highest ratio. It means that the rate of compression is much higher than the rate of elastic rebound over here. So in this case, we can see that at the highest contamination rate at 6%, approximately 98% of the increase in the compression index was observed. Similarly, 114% was observed in the relative density for this 70% in comparison to the clean sand over here. So here is the representation of the modification of the yield stress. So basically, yield stress can be a point where we can see that at which stress level the plastic deformations are occurring. So as we can see for the loose state, the yield stresses are reducing. So it means that the plastic deformations might occur at the low stress levels, whereas quite the opposite behavior is observed in the dense state. And at the 9% of the contamination rate, both are approximately to each other. Now, this can be indicated that because although the specimen is already in the highest compression behavior, so this is what it can be related to this increase, that why the plastic regions are occurring at the higher stresses in the dense state over there. Now, here is the variation. Here are the points of the yield stress, and we can see that after these points, how the stress behavior is being projected. Whereas in the figure number 14, C and D, this is a variation of the void ratio at yield stress. And as we can see that it is still keep on decreasing, although we have mentioned that here at the dense state, this is keep on increasing, yet the void ratios are reducing with an increasing percentage of the contamination rate. Now, here is the, in this figure number 15, it's showing us the how the volume compressibility is changing with the stress levels. So obviously at the low stresses, the highest, the low stresses, the compressibility is the highest. And as the stress levels are increasing, the compressibility is increasing as well. So we can also observe that for the 6% of the contamination rate, we even observe the least odometric modulus, which is basically the inverse of the volume compressibility representation. And we can see that in comparison, no matter what is the state of the soil, either it is loose or dense, the 6% of the contamination rate yielded less stiffer soil. And it is in all the cases, it is presenting the power law variation for both the compressibility volume and coefficient and the odometric modulus. So here are the results for the saturated state, and similar type of behavior is observed. So it means that that behavior is generally applicable for the 9% of the contamination rate, that it will in fact improve a little bit of compressibility characteristics. But upon looking at the compression index, there is not much a difference between the CC values of the 6% and the 9%. So again, this is in the range of the index densities. That means that again, the pre-crushing behavior was not observed as well before and after the test. The similar type of variations are observed, but in this case, the compression index values have significantly increased when we compare it with the dry state of the specimens tested. But nevertheless, we can see that although in the previous cases, our compression index for the 6% it was much higher in the, as compared to the saturated state. For example, in this case, we observed 35% of the increase in the compression index as compared to the clean sand. So similarly, for the dense state as well, a much lower increase in the compression index is observed in comparison with the dry state. So it means that in the dry state, the contaminations are in fact more and more actively playing its role. Again, similar observations are recorded for the yield stress. The plastic deformations are occurring again. If we look into the white ratios of the yield stresses occurrence points, the plastic deformations are occurring much earlier in comparison to the clean sand over there. So here the 6% have yielded the highest in the dense state again, which is again the similar response as compared to the dry state of all the specimens tested. Again, interestingly, when we see at the loose state, there's not much of a difference in terms of the odometric modulus, in terms of the stiffness of the soil in all the contamination rate, apart from the clean sand, where we can see that all the contamination rates had yielded higher compressible behavior at the low stress levels. So it means that in this case, the hydrocarbons are in fact playing interactively with the water molecules which are present in the sand matrix as well. Whereas in the dense state, only the 6 and 9% have shown higher compressibility and lower stiffness of the soil matrix. So in fact, when we look into the comparative analysis of the both dry and the saturated state curves, for example, these black lines are representing the dry state and the blue lines are representing the saturated state, we can clearly see that the saturated states have yielded higher compressible behavior. Why it could be? It is clearly related with the initial settlement upon the inundation process. So also we can clearly see that the initial compression behavior is also higher as compared to the dry state. So basically here we can take into account the buoyancy effect of the soil matrix. I mean that the sands are during the inundation process, the air molecules are basically eliminating within the soil structure, and that's why hence we have much higher compressible behavior in the saturated state. But interestingly, the shape of the curves also tells us an interesting story. For example, when we compare the clean sand with the 6% and 9% of the contamination rate, we can see that it's a trilinear curve, both in the dry and saturated state. So, it's a trilinear curve in the dry state, whereas it's a bilinear curve in the saturated state. So in the dry state, although we cannot say that these are for example, we have 3 different elastic zones. No, in fact, we can clearly investigate over here that what is happening in the first, second, and third zone. So for the first zone, at the end of the first zone stress level, the particle orientations are changing, and then again at the end of the second stress zone, the particle orientation are changing again. So this can be another interpretation on these kinds of graphs generated for the 6 and 9% of the contaminated soil compressible behavior. Whereas the typical curves are observed, the typical curves are observed for the clean and the 3% of the contamination rate. So here is the comparative analysis of both the CC and CR values for the dry and saturated state. And as I mentioned earlier, the dry states are yielding a higher compressible behavior in comparison with the saturated state when we talk about the compression index. Similarly, for the rebound index, it is the same behavior, whereas varying response is observed for the dry state. But apart from this, in all the cases, the 6% yielded much higher compressible behavior in comparison to the other soil groups. So talking about the cyclic behavior or the repeated loading conditions, we can see that, for example, how the graphs are changing. But interestingly, we can observe that at the end of each cycle, they are approximately the endpoints of the first cycle of the each testing groups. So we have applied in total 5 cycles, and the 6th cycle we applied is for the validation purpose, as it shows no significant varying behavior in comparison to the 5th cycle. So here at the 6% of the contamination rate in the dense state, it has in fact crossed the limiting conditions of the Emax and E minimum range. So it would be interesting to see that how the particles shapes are looking after the tests in this case. Other samples are within this Emax and E minimum zone. So most apparently there will be no crushing of the particle sizes occurring. So here is the variation of the compression index with the number of cycles. As we can see that if we with an increase in the number of cycles, the compression index is increasing, which is the obvious behavior we can interpret because the specimen is densifying with an increase in each cycle. And we can similar behavior can be associated with the rebound index. But interestingly, for the 6% of the contamination rate, the rebound index is increasing with an increase in the number of cycles. So this can be interpreted in terms of the, for example, the compressibility behavior which we observed in the previous slides, that the 6% yielded the higher stresses. So if we keep increasing the number of cycles, the specimens are under more stress and more in its limiting conditions, and they are elastically rebound after each number of cycles. So there is a constant variation at 2 and 3 and 4 cycles, and at the end, at the last cycle, it starts to decrease as well. So here you can see the compression index to the expansion index ratios. Again, at the 6%, these are the highest ones which are interpreted from these graphs. But the highest elastic recovery we can associate is towards the 3% and the 9% as in the last 2 cycles, as you can see in these figures in this table highlighted. So here is the variation of the yield stress with the number of cycles. And interestingly, at the first cycle, we have, for instance, like for the clean sand, 200 kilopascal of the yield stress. Upon the second cycle, it increased. Now, why in all cases, the yield stress has increased the second cycle? If we look into the graphs of, for example, for the clean sand or any contaminated soil behavior, we can see that although the compression index has reduced, but the initial slope is increasing. So that is the possible behavior. That is the interpretation why the yield stresses are in fact increased at the second cycle, whereas at third, fourth, and fifth cycles it tends to reduce in all the cases. At the end, approximately at the fourth cycle, all the soils are yielding towards the same values of the yield stress. So in this slide, this is the variation of the odometric modulus with cycles. So in this comparative behavior, we can see that the at the end of the last cycles, or let's say from starting from the third cycles, the highest odometric modulus, but for the 6% of the contamination rate, it yielded the lowest stiffness in all the cases in comparison with. So this is probably because this is due to the fact that the at 6%, it is more actively playing the role where more and more sliding between the particles are occurring, and which is yielding towards more and more compressible behavior for the 6% of the contaminated soil. So I will conclude my presentations. I will conclude my presentation with the following points. Our primary aim was to investigate the compressibility characteristics of the beach sand, which we collected from the Famagusta Bay, and it is containing carbonates, and we artificially contaminated our soil with 3, 6, and 9% of the petroleum hydrocarbons. And the specimens were reconstituted at 35 and 70% relative densities for both dry and saturated states of the specimens. So the key findings of this investigation were the compressibility was significantly increased with an increase in contamination rate. However, it was reduced at 9%, but nevertheless, this 9% reduce was in between 3 and 6%. And we cannot say that, for example, this a lot of the hydrocarbons are seeped out of the a lot of the specimens are seeped out of the soil matrix. But in fact, when we looked at the curves are approximately similar to the 6% of the contamination rate. And apart from that, saturated state higher compressibility characteristics, but nevertheless, the dry states were in the contamination in the dry state were more actively playing, as we can see that the CC was 98% increased in the loose state, whereas 114% increased in the dry state for the dense state, respectively. And the contaminations will cause the plastic deformation at lower stresses, regardless of the testing conditions, either it is in the dry or saturated state. And when we look upon the cyclic behavior as well, it is again yielded in more and more compressible behavior, because initially in the first cycle, the hydrocarbons have played more actively role, and that's why those behavior were reflected in the second, third, and fourth, and others cycles as well. And the final conclusion can be the 6% contamination yielded the lowest stiffness in comparison to the other testing groups. That's all from my presentation. Thank you very much for your listening. Thank you.
Thank you very much, Dr. Hamza. Perfect presentation. Let me ask if anyone has any question. Any questions? Okay, since no questions, I would like to move to our next presenter, Mrs. Hanene Marachi, that will going to be presenting the paper titled Compression of Groundwater Recharge Estimation Methods in Semi-Arid Upper Cliff in Algeria. Yes.
I'm Hanan Marouchi, PhD student at Hydraulic University of Hasiba Ben Bouali Shlef in Algeria. Firstly, I want to thank organizers of the 6th International Conference on Natural Resources and Sustainable Environmental Management for giving us the chance to present my work about comparison of groundwater recharge estimation methods in semi-arid upper she-leaf alluvial aquifer in Algeria. So, groundwater resources in upper she-leaf's plain present major sources of water supplies. It ensures both of water demand of urban, industrial, and special irrigation purposes, which consume a volume of 100 million meter cube each year. In front of this situation, characterize the groundwater recharge like a renewable water aquifer process is recurred. Estimate groundwater recharge is important for the evaluation of groundwater resources, budgeting, conservation, and water balance estimation. Several methods are proposed to computing groundwater recharge. In the present study, chloride mass balance methods for saturated zone and the unsaturated zone, empirical relationship between soil permeability and surface electric resistivity methods. In addition, the verification of the presence of accused recharge by Wadi Shilif in the western part of the study area are adopted to estimate groundwater recharge in this region. Let's start by a presentation of our study area. Geographically, the Upper Sharif alluvial plain is located about 120 kilometers south of Algiers, the capital of Algeria. It's covered an area of 348 kilometers square. Its northern border is defined by the Kar Massif, the Jindal in the Thorshat, in the south by the Wansharis chain, and in the west by the Arifs and the Wpmc. Point of view climate, semi-arid climate prevails in this region with an average international precipitation of 395 millimeter. The average air temperature is about 90. The Upper Sharif plain has an agricultural vocation with several towns where groundwater is principal source for domestic use, drinking, and agricultural irrigation. The structure of the hydrographic network shows an average density due to the low topography. Most of the hydrographic network is dry throughout the year, except during seasonal rains and wastewater, which is evacuated directly in the wadis without treatment. Geological context. The Upper Sharif plain forms a syncline of west-east orientation in the Italian Atlas. Stratigraphical succession in the study area from the older to the recent formation are the primary, the Jurassic, the Miocene, the Neopliocene, the Quaternary, and the alluvial finds, which are developed in the slopes in the boundary of the plain. The recent alluvial deposits are formed by the pebble, gravel, clay, and silt, covered by an organic soil. There is also the alluvial plain observed just near to the wadi bed. Aquifer system in this plain can be considered as multi-layer aquifer system. We note here that we are only interested in the quaternary alluvial aquifer. Groundwater of this alluvial aquifer flowed toward the center of the plain where the main drainage axis is located, which coincides with the Wadi Shilif, which is in blue. So, Wadi Shilif with a main flow is from east to the west. The depth of water table is from 5 to 30 meter. So, based in many studies of the subject, groundwater estimation methods can be divided into 5 basic sections. Water budget methods based in surface water data, physical methods which can account for saturated or unsaturated zone. We have also tracer technique which can be chemical, isotopic, or thermal tracer. And finally, modeling methods which can be numerical or combined, and so on. How come now to discuss how to choose the sustainable methods for quantification or for determine estimate the groundwater recharge. Choice of estimate methods. So, the characteristics of the study area and the purpose of the recharge study play an important role in the selection of quantification methods, where the objective determines the spatiotemporal scale. For example, the assessment and management of groundwater resource requires an estimation of recharge rate in a large surface as well as temporal scale. When the estimation of the transport of contaminants and the vulnerability of aquifers to contamination, which requires an assessment of a local and intermediate spatial scale. Also, the natural and availability of data required or technique relying in data. According to this criteria, three main methods of groundwater recharge estimation were chosen for our case. Firstly, the modified chloride mass balance methods applied for the saturated and the unsaturated zone. Secondly, empirical relationship between soil permeability and surface electric resistivity methods. And finally, geochemical mass balance methods applied to a section of wadi shelf. Let's start by the first method, which is CMP. The CMP methods use chloride anion to calculate the right recharge. The chloride anion are divided from both surface water and groundwater and from precipitation. The method is developed by Nrsem in 1969. It's based in the assumption that the only source of chloride anion in the unsaturated zone is precipitation. As few plants can use this anion, the concentration of chloride increase in the soil until the aquifer is reached. The recharge rate therefore decreases as chloride concentration increases. So, knowledge of the average chloride contained in precipitation or in precipitation and irrigation, and that of groundwater by the application of the chloride mass balance. So, if you know the chloride contained in precipitation and groundwater, we can apply it, we use the CMB method, the chloride mass balance. If we can obtain, or if our case or our study area are agricultural vocation, we use the chloride or the modified chloride mass balance. Here we need to use the chloride content of precipitation and also of irrigation. So, however, knowledge of precipitation and irrigation content, groundwater and that of soil pore water, makes possible to calculate recharge by applying the chloride mass balance modified chloride mass balance methods. It's according to the source of chloride. So we can use the equation 1 and 2 to calculate the recharge. There we show a summary of the methodology. As you see, for the CMB separated zone technique, we took sampling of rainwater, groundwater, and irrigation water using the equation 1. Recharge can be calculated for each point. Then we use the ADDY technique of interpolation to establish a map of recharge. So the average recharge calculated by this technique is about 10 million cubic meter. By the same procedure, only there the chloride content in groundwater is replaced by that of soil pore water for the CMB insaturated zone. And the map of repartition of recharge can be also established. By this method, the recharge calculate is about 36 million cubic meter. There is a summary of our work from the sampling phase to the determination of the chloride concentration. Coming now to the second method, the recharge, groundwater recharge estimation using empirical relationship between soil permeability and surface electric resistivity method. The recharge rate estimating due to rainfall was carried out using an existing model equation. This was done using one of the empirical models of groundwater recharge given by Fitter 2001. The formula is expressed as recharge is equal to the annual precipitation which multiplied by the open land portion. It means the area that has not been boiled open, which multiplied by the soil absorption coefficient in percentage. To determine the CR coefficient, that is in direct relationship with permeability of soil, which in turn is related to the resistivity of the same soil, the following steps are followed. Measuring permeability of 8 points of different type of soil in the plain by applying double ring method. Get the surface soil resistivity measured from vertical electric sending methods. Drawing the point cloud of measured permeability in terms of resistivity measured. Add Tunda's curve correlation and choose the correct correlation between the two parameters, which is the regression equation and the correlation R2. Derive the permeability from the measured resistivity values using the regression equation and using the description given by Bendix and al. In 1948 and Alport 2007 in table 1 to derive the CR, means the coefficient of absorption, according to the permeability range using the table 1 as I said. So once the CR coefficient is determined, CR distribution maps of the plane can be created using ArcGIS, and the recharge can be calculated using the equation 3. So this is our result: empirical relationship between soil resistivity and permeability, derived of permeability according to the resistivity, the spatial variation of range of permeability, and finally spatial variation of the absorption coefficient. The recharge calculated by the equation 3 for every surface are showing. So the average recharge calculated by the methods is about 10 million cubic meter by this method. The third method is the geochemical mass balance methods applied to section of Wadi Shelif. The objective is to characterization of the hydrogeological and geochemical relationship in the northeastern of the upper Shelif alluvial aquifer, determine probabilistic contribution fraction of the groundwater recharge by surface water from Wadi Shelif section passed through the commune of Jindal. So, mixed moderation of Wadi water, precipitation water, and groundwater were calculated for 5 wells using the natural preservative tracer CL introduced into the equation proposed by Igor Karvolosic et al. In 2022. As you see, the fraction is in relation with chloride content of sample water. It means water of Wadi, not Wadi. Sample. It means the water of underwater, of groundwater sampling. Also, chloride precipitation, chloride in surface water. The identification of recharge flow path requires a justification of the presence of continuous physical content between Wadi Shelif and the alluvial aquifer, which ensure the connectivity of the water between them. For this, we established a geological section of Wadi Shelif at the level of station of Jindal. Again, geophysical section of the region which cross both Wadi Wassan and Wadi Shelif gave us a view of the fixation of the formation in depth. In addition, the lithology sections of the few boreholes distributed around the sampling point are used to confirm the geophysics information. Chloride concentration in all samples exceeded the maximum contaminant level, which is 250 milligram per liter. So, when the geophysical, geological, and lithological section analysis in the region confirms the presence of physical environment which ensure the transfer of water from Wadi 2 kilometers around, fraction can be calculated. The possible mixing proportions for the chloride tracer can be calculated for the 5 observation wells using equation 4, and the results are presented into the figure. As conclusion, the application of the CMV methods for saturated and unsaturated zone allows an estimation of real diffuse and potential diffuse recharge respectively. The high concentration of Cl in groundwater makes the calculated recharge very low. The presence of sources or additional sources source of contamination of the water table via untreated wastewater evacuated directly in the wadis, as well as septic tanks, or even by geological formation caused and dissolution of rocks containing clay such as halite can be the cause of this estimation. Another source of recharge can also be justified as saddle and adduced by fluid and by surface water, which is wadis. The second methods present enable quick and low-cost estimation of groundwater recharge rate over the large area and is based in soil resistivity measurement. A few soil permeability measurements are required to establish an empirical relationship between permeability and resistivity. The permeability is then related to the groundwater recharge rate in the basis of theoretical consideration and annual precipitation data, or the different section studies. The gross groundwater recharge rate in the area, or the average groundwater recharge in the area, is about 10 million cubic meter. Result of the third method show that surface water is a key of groundwater recharge in the study area, which contribution rate ranging from 56% to 85%. The geological and hydrogeological condition which favor or limit water transfer from the wadis to the aquifer as verified. The last technique has provided that the recharge sources in the wadi effectively the results support the theory that increase in aridity reduce direct recharge and increases indirect recharge more in terms of total recharge to an aquifer. Is it to note that when we say direct recharge, it means the recharge which coming from surface unsaturated zone and reach the aquifer, while the indirect recharge is the indirect recharge is the recharge which coming from surface and saturated zone and reach the aquifer, while the direct recharge is coming from interaction of surface water and groundwater. Thank you for your attention. Sorry to deposit the time, and have a good day. Thank you.
Thank you very much. Thank you very much for this presentation. Mr. Binhaz, are you ready? Binhaz, are you ready, doctor? Sorry, miss. Can you please open your microphone?
Hello, everyone.
Hello, yes.
I'm ready.
You're ready. Can you open your camera?
No, unfortunately, I can't.
Okay. So, can you present your paper? You know how to present?
Yes.
Okay. Okay, so now I would like to call Ms. Binhaz to present the paper titled Integration of Artificial Intelligence with Environmental Biosensors. Ms. Binhaz, if you can please share with us your presentation and start. Hello. You hear me? Ms. Binhaz, your microphone is off. If you can please turn on your microphone so we can hear you. Hello. Ms. Binhaz, if you can open your microphone so.
Wait a minute.
Okay, take your time. Please try to make your presentation in full screen. So simply press present, share screen. Yes, put it in read mode, please. Reading mode.
Okay. Hello everyone. Today I want to discuss a
Sorry.
topic.
But still the presentation is not in full screen. If you can put it in read mode.
What?
Your presentation is not in full screen mode. If you can put it in full screen mode, put it in reading mode.
It's in full screen.
No, we see it as we see it's not full screen. So simply click present, share screen, then window, select your PowerPoint, and then set your PowerPoint to reading mode. Then we will be able to see it in full screen. Don't put view mode. Instead, use reading mode.
Could you see?
Just 1 minute. Yes, reading. The one like an open book. No, yes, this one. Yeah, that one. Yes. I think this is the one. Yes.
Okay.
Thank you. Go ahead.
Today I want to discuss a topic which is about integration of artificial intelligence with environmental biosensors. I will discuss these topics like biosensors, environmental pollution, traditional and current methods of environmental monitoring, role of artificial intelligence in environmental monitoring, advantages and disadvantages of using artificial intelligence, challenges and future work, and conclusion. First of all, I want to describe the definition of biosensor. Biosensor is a device that detects, transmits, and records information regarding a physiological or biochemical change. It has three parts. The first part is biological detector or materials, which they can be enzymes, tissues, microorganisms, cells, acids. The second part is transducer, and the last part is processing unit. We have many types of biosensors, but today we will focus on environmental biosensors, which can detect the contaminants in the nature like air, water, and soil. They are sensitive and they can detect contaminants even if in a trace amounts. The increase in population and the high demand of using technology by humans will cause environmental pollution, which will affect human health and the destruction of the environment. Human activities can cause four types of pollution like air, water, soil, and noise. Well, in the past, we had some ways to measure the contaminants in the nature. They used high-pressure liquid chromatograph, gas or liquid chromatograph mass spectrometry for detection and determine of pollutants in environment. However, nowadays we use biosensors, and I discuss some of why we choose biosensors. The most important of that, we can say, it has a great ability for portability, and they can measure a pollutant with minimal samples. As a result, they have high specificity and also high sensitivity. and the last thing, minimal size of them. One of the most promising applications of artificial intelligence in environmental conservation is monitoring environment conditions. Artificial intelligence can analyze large amounts of data from satellites, sensors, and other sources to provide real-time information on environmental conditions. As artificial intelligence become more integrated into our lives, it is essential to explore both the positive and negative impacts on our planet. As the world continues to evolve, so does the use of artificial intelligence. While it has the potential to revolutionize industry and change the way we live, it has also an impact on the environment. Let's start with the positive impacts. Artificial intelligence can be used to optimize energy consumption, making buildings and homes more energy efficient. It can also be used to monitor and reduce waste and to optimize transportation and logistics, reducing carbon emissions. Furthermore, it can also be used to improve the way we generate energy by analyzing large amounts of data and can help us better understand weather patterns, optimize the planet and operation of wind turbines and solar panels, and make our energy systems more efficient, as well as it can help us better understand and protect the natural world. However, it has some negative points. One of the biggest concerns with artificial intelligence is its energy consumption. Artificial intelligence requires a lot of energy to function, and that energy often comes from non-renewable sources such as coal or natural gas. The energy used to power data centers. The high levels of electricity consumption result in large amounts of carbon emissions, contributing to climate change. Without these points, using artificial intelligence is still more advantageous. We are faced with several challenges related to artificial intelligence and biosensors, as you can see in the diagram, and I explained some of them. First of all, data privacy and security, then technical limitation, and also technical expertise, and the high costs we can face. World Health Organizations as well as environmental protection should take biosensors in environmental monitoring and tackle the problems to reduce the amount of pollutants. Overall, the modern environment requires sensitive and accurate detection of the analyte. So the growing field of biosensors and the integration of them with artificial intelligence represents the best answer to this demand. Thank you for your time.
Thank you very much, Mrs. Binhas. Nice presentation. Any question for Ms. Binhas? All right, since no questions, I would like to invite our next presenter, Ms. Halima Budra, to going to be present the paper titled hydrochemical assessment of thermal waters. Yes. Thank you. Next video. Yes, our next presenter, Mrs. Halima Mutwa, paper titled Hydrogeochemical Assessment of Thermal Waters from Bohajer Geothermal System, northeast of Algeria. Okay, I think it's not ready yet. So I will invite instead Mr. Yes, Miss Halima. Actually, okay. So Miss Halima is ready. So we're going to watch Halima's presentation. Next. I think the voice is not coming. Okay, I think we have a technical problem in Mrs. Halima's video's voice. So I would like to move to next presenter, Mr. Alexei, going to be present a paper titled Optimization of Maintenance and Chemical Cleaning Methods for Separators Seawater Desalination Plants. Okay.
Authors conducted comprehensive research spanning freshwater production, water treatment, and maritime safety. Their work addressed the challenges related to sustainable technologies for freshwater generation, innovative water treatment methods, and the impact of various factors on water quality and safety. Additionally, they explored advancement and desalination technologies, included chemical cleaning methods for heat exchangers, and investigated ecological interaction in freshwater environments. The use of freshwater on board the ship, chemical reagents for water treatment in evaporator units ensure long-term prevention of clogging of heat exchange surfaces of these units with scale deposits, and also maintain the purity of the distillate obtained during the desalination of ship seawater and operation on brines with a high salt concentration. The dosage of these reagents is carried out in strict accordance with the instructions developed for each substance, taking into account its specific application. The choice of reagent for chemical cleaning of plate heat exchanger depends on the nature and composition of the scale. The successful result of equipment washing and its further operation depends on the precise selection of the reagents. The chemical agents for evaporator cleaning include next components shown in a table 2. Cleaned heat exchangers with acid involves the careful selection of acids as reagents that effectively remove specific scale deposits. Acid cleaning of heat exchangers encompass a range of reagents with sulfuric and hydrochloric acid solutions, as well as concentrates or condensates of organic acids like phthalic and citric acids, being the most popular today. While this method is effective, it poses certain risk. The production of hydrogen during acid cleaning creates an explosive mixture when in contact with air. Continuous monitoring of oxygen levels in the equipment and removal of excess oxygen are essential during acid cleaning. Cleaning the plates is carried out inside the heat exchanger using chemical reagents and special equipment. This method is quite economical, productive, and allows maintain the maximum performance of heat exchanger and extending its service life. Disassembly chemical flashing of plate heat exchangers involves several stages. Disassembling and removing the plates from the heat exchanger, immersing the plates in a special selected solution to dissolve deposits, flushing the device with water, reassembling the heat exchanger. This process can be performed either on board a ship or in service centers. The plates are extracted from the heat exchanger that immersed in a carefully chosen cleaning reagent as it's shown on this figure. This method is the most expensive among those mentioned. In conclusion, I like to say that the chemical cleaning of evaporators and heat exchangers necessitates vigilant monitoring of the cleaning solution's composition. Regular analysis enable timely adjustment, and chemical indicators aid and in monitoring the reaction environment. The processing strict adheres to instruction for each chemical agent and the chosen cleaning method.
Thank you very much. I think this was the end of Mr. Urkash's presentation. Thank you very much for listening. I think that's it for Mr. Urksai now. Let's try again with Mrs. Halima's video. Okay, I think we are having a technical issue with Mrs. Halima's video. I think that will be it for this session. Thank you very much for your attendance, your attention. Thank you, and see you in the next session after 30 minutes.
Hayat hızla akıyor ve biz bu hızı seviyoruz. Her güne heyecanla başlıyor, her anı doya doya yaşıyoruz. İlk günkü heyecanımızla yılları aşıyoruz. Zaman akarken biz de kendimizi arıyoruz. Heyecanla, merakla. Sen de kendini mi arıyorsun? O zaman zamana yetiş. Bu sadece kendini bulmakla ilgili değil. Asıl heyecan kendini yaratmakta. Bir şeyler mi yaratmak istiyorsun? Mükemmel. Metali işlemeyi, bir bina yapmayı, bir iş kurmayı, hatta bir şehir kurmayı öğren. Hayat kurtarmak, teknoloji geliştirmek, üretmek. Hepsi burada. Ve burada tüm deneyimler profesyonellerle yan yana. Ancak hızlı ilerlemelisin. Çünkü bugün şimdi gerçekleşiyor ve yarın çok yakın. Hayatta öne geçmek istiyorsan önce zamanın önüne geçeceksin. Hep ileri gideceksin. Bu Doktor Suat İrfan Günsel. Tanıyor musun? Onun da söylediği gibi. Üniversiteler toplumların dokuma tezgahıdır. Toplumları geliştirir, dönüştürür ve gelişmesini sağlar. O burayı bugünden yarına hazırlamak için kurdu. Senin için, ileriye gitmek için. Yana ya da geriye değil. Sadece ileri. Çünkü gelecek çok yakın. Hadi harekete geç. Fikirlerin ne kadar ileride olursa yarına o kadar yaklaşırsın. Yanındakileri de geleceğe taşırsın. Bu senin geleceğin, senin fırsatın şimdi. Hadi yarın yakın. Hepimiz